All right.
It's a phase red.
Okay. So this is the second part of the training course, which will be focused on the numerical formulation of self-model. Okay. I always, when I teach numerical methods, I always start by reviewing available numerical methods for solving partial differential equations. So I like to go over those methods, two of them very briefly. The finite difference method is, of course, very popular, and it's also one of the simplest. In finite difference method, you use the Taylor series expansion to approximate the differential operators. And finite element methods I usually apply on a structure grid. Okay, so structure grid for in 3D, for example, a pair of integers are sufficient to represent the location of a stencil. Okay, so if you look at this picture, we are now on slide 2. By the way, if you look at this picture here, this is a classical Arakawa C grid. So you with the 3 points in the horizontal and 3 points in the vertical, you can approximate the x and y derivatives. That's just straightforward. And because you have to somehow truncate the Taylor series, no matter how high order method is, you have to truncate at some point. So with that comes truncation error. So truncation error leads to the consistency issues. Okay, so if the truncation error goes to 0 as you refine the grid and the time step, then method is called consistent. So that means your discretized equation will approach to the original PDE, the partial differential equation, but then does not guarantee you'll get the true solution. Does not guarantee that numerical solution will also converge to the true analytical solution. But fortunately for linear system, we have this Max theorem that says a method, the numerical method is convergent if it's consistent and stable. Okay, this is for linear system. So this brings us to the concept of stability of the numerical methods. A numerical method is stable if the errors, however they are generated, will not magnify, will not increase over time. Okay, so of course the numerical stability is a big issue in numerical analysis. Okay. So lastly, I'm sure most of you are familiar with this idea of upwind for solving this advection diffusion equations. So upwind is actually a method to treat the advection term. So if you look at this, which is this equation, which is a discretized a pure advection equation, u is the advective velocity. So you can see that the first derivative is discretized in the upwind direction. Okay, depends on which way the signal comes from. Yes? Any questions? Oh, okay. Okay.
Okay. So these are numerical methods.
We are now on slide 2. Okay.
Okay, thank you.
Yeah. So the upwind method is, of course, has the advantage of get rid of unphysical oscillations. Okay, it's a first order, but it's very diffusive. Introduce lots of numerical diffusion. But the advantage is that it guarantees maximum principal and has no numerical dispersion. Sorry. Okay. So the second type of a method is called finite element method. The finite element method can be applied to the structure grid or unstructured grid. On the background, you can see an example of unstructured grid. Okay, so finite element is a really generic method, because the unstructured grid, structured grid is nothing but a special case of a structured grid. Okay, can be viewed as a special case here. So finite difference method, a finite element method treats the approximate the PDE in a different way. Instead of using Taylor expansion, it constructs the so-called weighted residual statement. First of all, you approximate the solution, the unknown, by a trial function. And then you construct this kind of residue. Okay, you plug the trial function into the original differential operator, you get this residue. Okay, because the trial function is not the exact solution. And then you take the inner product of the residue and a choice of a weighting function W. Okay, so this is the inner product. And try to minimize in some way. Okay, either using collocation methods or using least square or other methods. Okay, so that's how you solve the unknown U here. And there are many types of finite element methods. Some popular ones include the Glerkin finite element method. In this case, the weighting function is chosen to be the same as a shape function. I will talk about shape function in the next slide. Okay, and then if you use least square, then you minimize this residue here. Okay, so it's the inner product between the residue and itself. So the weighting function is the residue itself. So you basically use minimize the epsilon square. So advantage of using Glerkin finite element method is that if the underlying differential operator is positive definite, okay, there's a definition for that. I'm not going into detail of that. But if the underlying differential operator is positive definite, then the resulting matrix is also positive definite. Okay, that's a big plus for a numerical method. So you can use very efficient solvers, especially for large matrix. And the advantage of using least square is that the mass matrix is always symmetric. Okay, that's also an advantage in numerical methods. And if you take this weighted residual statement, the inner product between the residue and the weighting function equals 0, that's collocation method. And if you just solve the equation as it is, form algebraic equation and solve it as it is, that's called a strong formulation. Okay, you are doing no manipulation to the weighted residual statement. On the other hand, if you do some manipulation, in the usual case, you do integration by parts and utilize the boundary condition, then you are basically changing the weighted residual statement. In that case, you are using a weak formulation. Okay. So shape function is a very important concept in finite element. They are primarily used to approximate the unknowns. Okay, so phi I are used to approximate the unknown U. Okay, Ui is the functional value and each load. Okay, for unstructured grade loads are defined as vertex of the polygons. So of course, in order to be shape function, the phi I must satisfy this consistency condition. So phi I evaluated. So phi I means the weighting the shape function associated with a particular point I in space, and xj means a particular the coordinates of a particular point j. So phi I xj equals a chronicle delta ij. That means the phi I is uniform in 0 everywhere except at the point where it's defined. Okay, that's the definition of a shape function basically. And if you use a weak formulation, you also want to make sure that your shape function is smooth enough, because when you do integration by parts, you need to take derivatives of the shape function. So one important thing about shape functions is that we typically use shape function within each element. So we are using the shape functions in the local region, but the concept of shape function is global. Okay, it's defined everywhere, except that well, it's defined everywhere but it's usually 0 outside the immediate region of interest. So for example, here are some examples of a shape function. On the bottom, you can see the one-dimensional case, the linear hand function and quadratic functions. And in 2D, you have this traditional linear function as hand function in the conformal sense. And this the second picture shows the little bit non-conventional, non-conformal hand function, which is discontinuous at each load, and continuous at side centers. Okay, those types of shape functions are gaining popularity recently because of their usage in finite volume methods. I forgot to mention that finite volume methods, of course, is gaining popularity, but it's nothing but a special case of finite element. Okay, so if you take the shape function to be piecewise constant, then finite element essentially becomes finite volume. Okay, so, and if anybody has questions, don't hesitate to ask. Okay, so I think the course will be most effective if you guys ask questions.
So in self are these various methods, shape functions, are they options you can choose?
No. Right now we are just using the linear hand function. Yeah, either formal or conformal, non-conformal shape functions. Because when you use higher order shape functions, the coding becomes very complex. But in theory, yes, you can extend. You can use quadratic in 2D. So in a 2D sense, if you look at this region around a particular load J, the shape function associated with this load J is 0 everywhere except 1 at this point. Okay, so if you can imagine in 2D, it's basically shaped like a pyramid. Okay, and outside this immediate region of concern, the ball of the load, it's everywhere. Shape function is 0 everywhere. Okay, so it's a global concept. Okay, don't get confused because most time we are using shape function in a local sense, but it's actually global quantity. So if you plug this approximation, the trial function, back into the differential operator, and if you use a Galerkin finite element methods, which means that the weighting function are the same as a shape function, you get this integral equations with unknowns ui. Okay, and then you need to basically form algebraic matrix equations for this ui. So one of the most time-consuming tasks in finite element methods is actually to assemble that global matrix, also called mass matrix. Okay, because you have to evaluate a number of integrals. And compared to finite difference methods, the bandwidth of the matrix resulting from a finite element method is usually larger. Okay, so in finite element method, sometimes people lump the mass to the central load. Okay, so-called mass lumping. So then, in order to reduce the bandwidth of the matrix, then you are basically essentially going back to the finite difference. Okay, so some people think that finite difference is actually a special case of finite element. So here are the quick summary of the self-model features. Self is based on semi-implicit finite element framework. And because it's implicit, so number of equations are coupled. In order to solve them efficiently, we found a method to decouple the continuity equation from the momentum equation through the bottom boundary layer. And self uses unstructured grid, the general unstructured grid, triangular grid in the horizontal, and the hybrid SZ in the vertical. And as its name implies, it uses ordinary Lagrange methods for momentum direction. So I will explain what EOM is in the next couple of slides. So numerical efficiency of self comes from the fact that three things: semi-implicit scheme, EOM, and of course the use of unstructured grid to efficiently resolve the domain. So there are still some remaining stability constraints resulting from the explicit treatment of a number of terms in momentum equation, like horizontal viscosity, ambient clinic pressure, etc. And compared to the older model L-circ, self is usually moderately more expensive, 30 to anywhere between 30% to 100%. And the reason is I just explained. Basically, L-circ uses finite difference methods. Okay, so whereas the self uses finite element method. So in order to use finite element method, you have to evaluate the number of integrals. So that's a time-consuming part. Also, the bandwidth of the matrix equation, that doesn't help. Okay. But in terms of convergence rate, for if you do numerical analysis for a uniform grid, yes?
Could you explain the stability constraint?
The numerical stability is basically, you know what numerical stability is, right? The errors never magnify. So whenever the rule of thumb is that in the equation, you can treat each term either implicitly or explicitly, right? Implicitly, that means you are treating it as an unknown, whereas explicitly, you are treating it as a known quantity. So if you treat a term explicitly, that usually will comes with some kind of stability constraint. Okay, whereas if you treat it implicitly, usually you bypass that constraint. Okay. So if you for uniform grades, the self is second order. Okay, and by default, but we have also implemented a number of optional higher order schemes in momentum and transport. And another advantage of self is that it treats the inundation really naturally. Okay, and of course we have applied the model actually, benchmark the model for tsunami inundations. So we are now on slide number 5. Those two pictures shows the examples of structure and unstructured grid. On the lower left corner, you can see the example of a structured grid, which is very easy to understand. A pair of integers determines everything. Okay, you know its neighborhood, you know the stencils. Whereas in an unstructured grid, then you have to specify not only the location of each node and how the elements are collected from each node, but also how elements are collected to each other, so-called collectivity informations. Of course, the advantage of using unstructured grid is that you are able to resolve geometry very well, and you can do a local refinement very well. Okay, give you lots of flexibility. So self uses a hybrid SZ in the vertical. So what does it mean? Okay, so essentially, originally we actually started with pure terrain following coordinates, S coordinates. Okay, and the Z layers are added later in order to bypass some difficulties when we do benchmarking, especially the Columbia River plume. Okay, so the Z layers are usually used in the deeper depths. So if you look at this slide number 6, on top you have a number of terrain following coordinates, 9s, whereas below this particular depth you have a number of Z layers. Okay, so the transformation, the S for the transformation is the same as in ROMs. Yes?
How do you determine where that is?
the HS, the transition depth between the S and Z is a key parameter in itself. Yes, you must choose it carefully. It really depends on applications. I must say that for most, say more than 90% of applications, I found that pure S is actually sufficient. You don't have to use Z layers to stabilize the solution.
And do you do anything different when you get to the very small bottom layer, like what's happening right at that boundary layer?
Boundary layer, the question, I probably should repeat the question. The question another one asked is that what do you do when you go to a bottom boundary layer in the shallow region, I guess?
Mm-hmm. Yeah.
In the shallow region, well, that's why we use terrain following coordinates in the shallow region. See, so the bottom boundary layers are always resolved. Okay. Whereas in the deeper region, if you use Z coordinates, then the bottom boundary layer may not be resolved. Okay, then that's just the nature of Z coordinates. Okay. So on the bottom, you can see the S transformation. That's the same as ROMs proposed by Song and Hayden-Vogel. So the only difference is that the water depth is restricted. So it's if you look at the equation, that's H tilde here. Okay, H tilde is a restricted water depth up to HS. They separate, they delimiting depths between the S layers and Z layers. Okay, so essentially you are allow the coordinate to follow the terrain up to certain depth, HS. Okay, and this function C is a very complex, involves transcendental functions, but it has two parameters in it, theta B and theta F. I'll explain what they are. And in addition, this S transformation also has a parameter HC. Okay, so this is basically separation depth between the S zone and the sigma zone, because if H falls below HC, then the transformation becomes singular. Okay, so what we did is we basically use the traditional sigma coordinates instead, because S coordinates becomes invalid. Okay, so if in the future somebody propose a new set of coordinates that are uniformly valid from a very deep to very shallow region, then we can easily switch to then coordinates. It's pretty trivial to do that. So next,
What's the term to
HC
HC?
is another important parameters. Depends on the application. For example, you want to make sure HC is large enough for plume applications, because HC, in the next slide I'm going to show you, HC actually also determines how large your boundary layers are, the depth of boundary layer you want to resolve. Okay, that's also determined by HC. So here we are now on slide number 7. So there are 4 pictures here showing you the examples of the S coordinates with respect to the 2 parameters theta F and theta B. As I didn't show you the variation with respect to the HC, but HC is a minimum depth used for S transformation, and also determines the layer thickness near the boundary where you want a fine resolution. So if theta F is very small, then S coordinates becomes traditional sigma coordinates. So you pick any point space, the vertical column is evenly resolved. Okay, that's the sigma coordinates. And if theta F is not small, then bigger theta F is, the larger the nonlinearity. So you have this kind of uneven spacing in the vertical. In particular, if theta B, you have a more coordinates line crowding towards the boundary layer. If theta b equals 1, the bottom and surface boundary layers are well resolved. If theta b equals 0, then only the surface layer is resolved and bottom boundary layer is not resolved. And theta b between 0 and 1 somewhere in between.
So
Yes.
is it fair to say that theta b, the surface, if theta f is sufficiently large, then theta b, theta b will affect how well the bottom is resolved? It looks like the surface is always fairly well resolved, no matter what theta b.
Theta b also, the question is, does theta b only affect the bottom resolution? The answer is no, because the choice of theta b also affects how fine you resolve the surface layer. Because whenever when you increase theta b from 0 to 1, more and more coordinates line will be crowded towards the bottom at the expense of the surface layer. Okay, so that's indirectly affected. So of course, in the typical coastal applications, theta b equals 1 is pretty attractive because you want to resolve both boundary layers. So next slide, slide number 8. So this is a transect view of the vertical resolution, vertical discretization. Okay. Again, HS is the demarcation depth between the Z layers and the S layers. So on top you have a bunch of S layers, so you can see that the bottom is resolved pretty well. Whereas if you go down to the Z layer, then the staircase bottom appear. Okay, that's just unavoidable.
But you have a way to deal with those gaps, right?
What gaps?
The staircase, when you start going staircase, the spacing.
Well, there are many ways to. The question is, how do you deal with this staircase? The answer is that there are many methods proposed to alleviate this kind of staircase profiles, but none of them are satisfactory. Well, that's why people like to use terrain following coordinates in coastal applications.
And that's why you said sometimes you can just get away with S layers the whole way through, right?
Oh yeah, if you can get away with pure S layers, by all means, because you don't have this kind of staircase profile problem.
So remind us what the disadvantage to having all S layers is, or why the Z layers are useful?
The question is, why do we ever need Z layers? Z layers are needed for certain applications. For example, the plume applications. So the S layers, the terrain following coordinates have this classical problem of pressure gradient error, which I'll explain later. Okay, so if you have a very steep bathymetry, then it can cause lots of instability. Okay, next slide, number 9. So the combination of horizontal and the vertical discretization leads to the basic computational unit in 3D being a prism. But in this case, a prism will have uneven surface and bottom. Okay, because the terrain following coordinates are used. And of course, the S coordinates are ideal for shallow regions, and Z coordinates are necessary to stabilize the deep regions. That's what we found out the hard way. And the sigma coordinates are used in place of S coordinates whenever needed. So another thing is that itself we do not transform the equations into S or Z sigma coordinates. Okay, we solve everything in the original Z space. So that simplifies the implementation of SZ hybrid coordinate system. And in many parts of the model, you need to do 3D interpolation, okay, in space. And we allow users to do that interpolation either along S or Z plane. Okay, so the bottom two pictures shows you the two interpolation mode. Okay, the first one you do interpolation along the fixed z-plane. Okay, so this is very intuitive, but of course it causes problem when you are below the bottom or above the surface. On the right, you can see the interpolation in the vertical along inside the transformed coordinate plane. Okay, this has an advantage of bypassing the difficulty near the surface and bottom. So this will bring us to eventually to this problem of so-called hydrostatic inconsistency associated with this baroclinic term. So I'll talk about this later. Slide number 10. So now let's go ahead and discretize the equations. Okay. And the major model is divided into two major parts: the barotropic part and the baroclinic parts. So we treat the baroclinicity term explicitly. So we basically we decouple the transport equation from the momentum equation. We don't solve them together. So the first part, the barotropic solver part, consists of two equations. They're coupled: continuity equation and the momentum equations. And first of all, we discretize them semi-implicitly. So n plus 1 is the next time step, new time step, and n is the previous time step. And the theta here, for the first equation, theta is the so-called implicitness parameter. If theta equals 0, you get fully explicit scheme, right? If theta equals 1, you get a fully implicit scheme. And theta equals 0.5, that's Crank-Nicholson scheme. Usually give you best accuracy. Okay, so so the first equation is discretized continuity equation only in time. We haven't discretized the variables in space yet. Okay, the second one is discretized momentum equations. And in numerical method, you want to differentiate what's unknown and what's known. So you want to group the explicit terms and you want to group the implicit terms. That's why I use this a bold F to represent all the explicit terms, like horizontal viscosity and baroclinicity term, and atmospheric pressure gradient term, etc. Okay, so the what's left on the right-hand side of the momentum equation are the pressure gradient term, delta eta. Eta is the free surface elevation, and the vertical viscosity term we treat implicitly. So, and next, of course, you have two vertical boundary conditions and free surface and bottom, and chi here is this product of drag coefficient and bottom velocity. So because we use drag law, we cannot, we don't want to solve nonlinear equations, so we treat part of that bottom velocity explicitly. Okay, either using the value from previous time step, or we can use the value from backtracking. So U star, yes?
Oh, sorry, this is kind of on the same way. When you treat something implicitly, I have a hard time seeing how those boundary conditions work. I was wondering if you could maybe go into a little more depth.
Okay, the question is, when you use the implicit scheme, how do you treat the boundary condition? If you look at the third and fourth equations, those are the two vertical boundary conditions, and they are being treated, they involve unknowns. U n plus 1, that's unknown on the left-hand side, right? And if you look at the bottom boundary condition, U b n plus 1, that's also unknown. So you can treat the boundary condition in a similar way as the other equations, the governing equations. You know, you can treat each term either implicitly or explicitly. Like I said, if you treat the terms explicitly, of course your life is easier. You don't have don't have to form equations, but that comes with a price. You pay the price of numerical stability. Okay. So in our scheme, we try to treat each term semi-implicitly as much as we can. Okay. For some terms like binary term, that's not possible because you don't want to solve a fully nonlinear coupled equation. That's just too much hassle. So we decide to treat it explicitly. So the key term here to notice is a U star. U star is basically used to approximate the total derivative. If you recall the lesson from previous time, this total derivative is a term in Lagrangian sense. Okay, you are following fluid particle, right? So it's not an ordinary sense. So this U star is a reflection of that. And we basically approximate the total derivative du dt by this simple finite difference in time. Okay, except now U star is no longer evaluated at nodes or no longer evaluated at nodes. It's in a position unknown, beforehand. So we are essentially taking advantage of so-called ordinary Lagrangian methods. So this goes back to the pros and cons of Lagrangian and ordinary methods. Ordinary methods, of course, is very easy to interpolate fixed in space, and the derivatives are usually much easier to evaluate. But the drawback of ordinary method, the pure ordinary method, is that usually comes with a severe stability constraint. Whereas Lagrangian methods does not have that much severe stability constraint. But the disadvantage of using pure Lagrangian method is that you have to deform your mesh. You have to make your mesh adaptable to the flow field. So each point in your mesh will become a particle. So as the particle moves, you have to move your grid. So the grid sometimes can become highly distorted and also sometimes even become a topology may even break down. So that's a disadvantage of using pure Lagrangian methods. So EOM is an attempt to take advantage of both methods. Okay, you still use a fixed grid. You don't let the grid deform, but you use Lagrangian methods to approximate the total derivatives. And so forgot to mention that for pure ordinary methods, if you use an ordinary method to approximate the advection term, this total derivative term, then you usually constrained by the so-called Coulomb number condition, which simply put means that within each time step, the signal cannot travel beyond one element. Okay, it's a simple interpretation of a Coulomb number. Whereas if you use EOM, you don't have this condition. In fact, if you implement EOM right, it's the only fully explicit method that's unconditionally stable. Okay, I'm not aware of any other explicit method that are unconditionally stable. So the way EOM method works is like this. You basically solve the this equation dx dt equals the velocity, okay, 3D velocity, backwards. You integrate this differential equation backwards in time and space. Okay, so for example, you start from a side center and t plus delta t, and you try to reconstruct the fluid path, or in EOM term, characteristic lines backwards in space and time, and try to find the originating space, this is originating position at previous time step t. Okay, so of course, and then you evaluate the variable and this position at previous time step t. Of course, there are lots of details in EOM. Okay, many people actually did a PhD thesis on EOM. So, but some important aspect of EOM involves how you do the tracking. Okay, you can either use a simplest backward Euler methods, or you can use more sophisticated, like a fifth order embedded Runge-Kutta method. Okay, and if you think about the advection diffusion equations, advection term, if you treat the advection terms in ordinary sense and use finite volume and in a flux form, okay, so I haven't talked about that, but the finite volume and the flux form usually conserves mass exactly, okay, in a numerical sense. But if you use EOM to treat then the advection term, mass conservation is not obvious. You are not enforcing anything. Okay, so but of course you can bypass this by using some kind of finite volume, control volume integration EOM, so-called, to conserve the mass. But in 3D, then the integration EOM becomes very expensive. So finally, we decided we just use the interpolation EOM. So very briefly, integration EOM means that you instead of take just one point and new time step, you take a bunch of points in a given control volume and backtrack them in space and time and get their originating positions. And then you do some kind of integration in that volume, make sure mass are conserved. Okay. So depending on how you do the interpolation, you can either have a numerical diffusion or you have a numerical dispersion. Okay. So this top picture shows the simple concept of diffusion and dispersion. Okay, so in a diffusion, pure diffusion sense, the amplitude will go down and standard deviation will become larger, whereas numerical dispersion will cause the overshoot and undershoot. Okay, amplitude will be too large in some place, and you have a negative mass in some cases. So lower order interpolation in EOM typically leads to diffusion. Okay, so your signal amplitude will go down, and then there may be unphysical. Whereas higher order EOM, interpolation EOM will lead to dispersion. So you have to find a way to get rid of all those undershoots and overshoots. Any questions so far for the EOM?
Joseph, I
Yes.
have a quick question.
Yeah.
This backtracking, you are doing three-dimensional backtracking, correct?
Yes. Yep.
Not just for like long, right?
Yeah. It's
So,
3D. Yeah.
3Ds. So in a vertical, do you have a, I mean, because vertical you are using sigma S or SG coordinate.
Right.
Do you feel that, if you're backtracking in a vertical also, there will be a problem? In a Z plane, I don't have a problem, but in a sigma plane, because you transform the coordinate and then you backtracking in. But I know the vertical velocity is usually very small.
Yeah, that's true.
I
but
just want to get your comment.
Yeah. Okay. The question is in 3D backtracking, because we are using hybrid SZ coordinates, would that cause a problem for the vertical velocity? So the answer is not really, because like I said, we in 99% of the case we actually use Z coordinates. We do not. S coordinates is basically a tool to generate a bunch of Z coordinates. Okay, we do interpolation in Z space.
Do interpolation in Z. Okay.
Yeah, that's right. Yeah. Okay, next slide, number 11. So let's apply the standard Galerkin weighted residual weak statement, okay, for this first equation, the continuity equation, discretized in time. Okay, then you integrate by part. That's the essence of weak formulation. Then you get a bunch of boundary integrals coming out now, okay, gamma. And you further divide the boundary into two parts, depending on not whether you have an essential boundary condition or it's a natural boundary condition. Okay, so you get gamma and gamma bar. Okay, the capital letters are typically used to denote the depth integrated quantity. So capital U is total depth integrated velocity, and phi I again are the shape functions, which is the same as the weighting function because we are using Galerkin methods. Okay, theta again is the implicit factor. So any questions from the audience, from the remote site? Okay. So, and phi I are defined and all the nodes, okay. Okay, so then you can see, yes?
Oh, I wanted, you have them separated this way. What are the individual terms, the sets?
Well, the reason I separate, I guess you are referring to the boundary.
Right.
The boundary. Mm-hmm. Okay, the question is why do I separate the boundary in this fashion? Well, because this will become clear, as you go on. But essentially, it's basically want to differentiate what's known and unknown. Okay, and if you, for example, on the natural boundary, the boundary segment where natural boundary conditions are imposed, then the velocity becomes known, right? So that's why I use U hat, capital U hat. That means it's actually known, although it has a superscript of n+1. Whereas on the essential boundary segment, then it's truly unknown, right? Right. So if you look at this equation, it has two sets of unknowns: the surface elevation and the depth integrated velocity. And so our goal is actually to eliminate the depth integrated velocity by vertically integrating the momentum equation. You get this. Okay. Again, in numerical methods, especially implicit method, you want to differentiate what's explicit and what's implicit. So I use capital G to basically group all the explicit terms into one term. Okay, because they are very straightforward to evaluate. So the implicit term include the pressure gradient delta eta, and because you integrate along the vertical, the boundary condition comes out. Okay, so the bottom boundary condition is chi delta t and ub. Ub is the velocity and the top of the computational cell. Okay, so now we apply the bottom boundary layer theories. Okay, so we have a bottom velocity ub here. We want to get rid of it. So what we did is we take the momentum equation and this position, and then because inside the bottom boundary layer, the Reynolds stress is constant, so the vertical viscosity term becomes 0. So we can formally express the ub, the bottom velocity, as a function of the unknown elevation, right? So you substitute this equation back to here. So the depth integrated velocity can be expressed as a function of unknown elevations. And then you substitute this integrated momentum equation back to the continuity equation. You get the one equation for the unknown elevations alone. Okay, so that's how you decouple the two equations. Now, number of quantities I like to explain. H hat is friction reduced depth. So it's total depth reduced by the friction. And if you look at the final integral equation, you have 6 integrals. But if you look at them very carefully, you can see that you don't really have to evaluate 2 of them, like I3 and I6. The reason is that I3 and I6, yep. Is that right? I3 and I6. No, I2 and I6, sorry. I2 and I6. The reason is that I2 and I6 are boundary segments where the essential boundary conditions are imposed. If essential boundary conditions are imposed there, the eta becomes known there. So you don't need equations for eta there, right? And in other parts, if you look at the other boundary segment or interior points, then phi I becomes 0. So these two terms automatically gone. So you don't have to evaluate them. So the only integral, only parts that has unknown elevations is actually I1, only one term. This really simplifies things. The rest of them are all explicit terms or known terms. Okay? So next slide, number 13. Let's look at each individual terms in detail. I1 is the only one really has the unknown elevations. So if you use the linear hand shape function, then you can discretize them and express them in this form, summations. Delta again is a canonical delta. And I prime is basically a position in a particular load. And L is basically it's a dummy variable here. So it's also denote a particular load, if you think that way. So, and the second term involves this dot product, I prime vector and L vector. So that's this dot product is a maximum when I prime equals L. Okay, when they coincide, the dot product becomes the maximum, right? And the canonical delta also is maximum when I prime equals L. So that gives you diagonal dominance. That makes sense? Okay. I prime equals L, that's your diagonal element. And in addition to that, if you sum up this second term, it's actually 0. Okay, it's actually 0 there. So it's diagonal dominant, but also it's also a positive definite, provided that this coefficient here, the average depth reduce, the friction reduce the total depth is positive or 0. That makes sense? So it's diagonally dominant and positive definite, provided that the depth, the modified depth is non-negative. And then in many applications, even this condition of non-negativeness can be relaxed. So in most cases, the mass matrix is actually positive, definite, and symmetric. If you look at the I1 in detail, it's actually symmetric. That's where the efficiency comes from. Okay, if you have a positive, definite, symmetric matrix, you can use a very fast solver to solve it, especially for the very large problem. And in this way, in this sense, self actually shares the efficiency with L-circ, because in L-circ the matrix is also positive, definite, and symmetric. So slide number 14. We have two, on this slide we have two boundary integrals, okay, defined on the lateral boundary now, I3 and I5. So again, you use a linear shape function, you can easily evaluate them. And if you decide to use flatter boundary condition, okay, in this form, whereas U bar and eta bar mean velocity and elevation field, then you can integrate them out using linear shape function. But be careful how you apply the linear shape function, because this one, if you use a flatter boundary condition, this I3 now include unknown eta n plus 1 here. Okay, so the way we treat it is such that this will enhance the diagonal, so wouldn't break the diagonal dominance, and it's also symmetric. Okay, so you must be a little bit careful there. slide number 15. So the last integral, I4 has the most complex form, has all sorts of explicit terms in it. Okay. So if you use the shape function again, you get this form. And Gj prime can be expressed in this equation. Basically has advection. First term is advection, and second term is all the other explicit terms like Coriolis and horizontal velocity, baroclinicity, horizontal and F2, F1, F2. Basically, you remember that explicit vector I use capital the bold F. We decompose into two parts, F1 and F2. So the capital F1 and F2 are the depth integrated quantity of small F1 and F2. Okay. So the and the inside the bracket you have a bunch of terms associated with the bottom boundary layer. So the most complex part is the baroclinicity term here, the FC term. Okay, if you look at this term carefully, delta rho is evaluated along the z plane, right? It's not along the train follows along the S plane. So this brings us to the issue of pressure gradient error. So this, of course, is a big deal in terrain following coordinates model. There are many papers actually proposing different ways of reducing the error. So the source of this error, pressure gradient error, comes from the fact that you are using chain rule to evaluate delta rho in Z space. So you basically express this delta rho as a difference between two terms evaluated along the sigma plane. Okay, and if both terms are large, then you can have large truncation error. That's the origin of a pressure gradient error. So, of course, the advantage of using this this so-called pressure Jacobi method is that you don't have to treat the bottom and the surface spatially because everything is in a transform domain. But the disadvantage is just what I said. You can have a pressure gradient error, and people have done lots of tests on this kind of isolated Simon test. Where you start with a stable stratification, and without any external forcing, the stable stratification should last forever. So people have tested their method on this kind of things to say if pressure gradient error play a role in their model.
So does
Yes.
that work very well for shallow? And is it going to be? Is there any difference in?
Oh yeah, that's a good question. The question is this pressure gradient, pressure Jacobi method, does it work differently in the shallow depths or deeper depths? Yes, I think in the shallow depths it's not a big problem. It's only a problem in the deeper depths, deeper part of the ocean. In a shallow like estuary, it's not a problem at all. So next slide. So in the most recent version of SELF, we actually choose to evaluate the baroclinicity term using the so-called Z-coordinate methods, okay, in order to bypass the pressure gradient method, pressure gradient errors. So in this method, we evaluate everything along Z plane. So advantage, of course, is to alleviate the pressure gradient errors. But this method does have a disadvantage of near and bottom and surface. You have to do some kind of special extrapolation. So the way we did this, we evaluate this baroclinic term depends on what kind of algorithm you use to solve the transport equation. I haven't reached the point to tell you what kind of method we use to solve the transport equation, but very briefly to give you a heads up, we use two methods to solve the transport equation. The first one, we just use traditional EOM to treat the advection, whereas in the second method, we use pure Euler methods, that's upwing and TVD methods. Okay. In either method, because we use Z coordinates, and we want to reconstruct the density gradient at a particular point. So the way we do that is to build the equations for the directional derivatives along two directions, okay, and solve for the two unknowns. So the first method we use to solve the transport equation is the EOM method. So in this method, densities are defined as nodes and hole levels. So suppose you want to evaluate the density gradient and the side center. So you build this stencil here, 1, 2, and 3, 4. Okay. 1, 2, and then you build the equations here. It's the equation system. Rho prime here, you notice, is demeaned density. We gave in the newest version of code, we gave the user the option to demean the density, because this rho bar, which is function of Z only, does not contribute to this gradient, right? This is horizontal gradient. So gradient of rho bar is 0. But then if you know the mean density profile, it helps a lot if you subtract the mean profile. So these two equations simply says the directional derivative along 1, 2, and 3, 4 must be equal to the difference between density difference along those nodes, right? And of course, if this side is happen to be a boundary side, then we just use a low flux boundary condition. Okay, there's no normal flux along the boundary. So you can replace one of the equation with a no flux boundary condition.
And these are not going to be equally spaced, right?
No, they can be anything.
Okay.
At 1, 2, and 3, 4, in unstructured grid setting, they can be the angle may not be 90 degrees. Can be any arbitrary angle, but they cannot be parallel to each other. So that's why this equation system always has a solution. It's well conditioned. Okay. And another key thing we did is to use QB spline to do the interpolation, because you want to evaluate the densities and fix a Z plane. Okay, you want to evaluate a Z plane, so you need to do interpolation. So this picture shows how the interpolation is done. So, and this green dot, it's the side centers and the hole levels. Suppose you want to evaluate, interpolate this points 3 here, and you use QB spline to reconstruct the density profile and 3 and interpolate onto this dashed lines. Okay, so the combination of QB spline interpolation and the demeaning of the density profile really helps reduce the spurious upwelling problem we discovered before. So of course the disadvantage of Z coordinate method is that you have to be careful with how you do extrapolation near the bottom and surface. Near the surface is not a problem because surface slope is not that big deal, but bottom slope can be very steep. So inside the code we give the user two options. I explain that two options when I talk about the code. But essentially, one option is more conservative than other in order to not to trigger those spurious flows. So that's for the EOM transport. Okay, so EOM transport has the advantage of as far as the bioclinic term is concerned, has the advantage of everything defined on the loads and whole levels, so makes things really easy. Whereas the next method to solve the transport equation, the TVD or the second order TVD, the upwind or second order upwind methods. Just a second, give me a mind. We started. Okay, great, thanks. So the upwind or second order upwind methods is a pure ordinary methods, and not only that, it's usually combined with finite volume. And if you know finite volume well, it's usually variables in finite volume methods are usually staggered. Okay, so that's not a good news for the bioclinic term, because you have to somehow do some kind of interpolation, back and forth. So in this method, density is now defined at the present center, okay, half levels. So what we did finally is to evaluate the density gradient and present centers first. Okay, basically construct this kind of, we are now on slide 18. On the top you can see the picture with triangle with 3 dashed lines. So we construct this kind of stencils to evaluate the 3 directional derivatives of the density. But because you only have 2 unknowns, so you have 3 equations for 2 unknowns, and that's an overdetermined system. So what we did finally is to just pick 3 pairs. Okay, the 3 pairs, get the 3 equation systems and solve them and average them. Okay, so that's the difficulty we are facing with the staggered methods, because you have to do this kind of interpolation and averaging schemes. Again, vertical interpolation is all done using cubic spline. And you can optionally remove the mean density profiles, rho mean. Okay, so if you pick this pair, say 1, 0 and then 2, 0, you can form this equation system just as you did for the EOM methods. It's basically 2 directional derivatives, and solve the unknown rho prime x and rho prime y at present centers. Okay, so you get one set of solutions, and you get another set of solutions for another pair like a 2, 0 and 3, 0 and a 3, 0 and 1, 0. So you just average them. And in this case, this stencil actually is not always well formed, in the sense that in some cases, for example, 1, 0 and 2, 0, they may be very close to be parallel to each other, because that's degenerate case. So in those degenerate case, we basically throw the equations out. We got too many equations anyway. So the cutoff angle we used finally is 1 degree. Okay, so if the angle is very close to 179 degrees or larger, then we just throw that equation out. And after,
Joseph,
yes.
How do you define the center of the prism?
The question is, how do we define the center of the prism? We basically just they average the top and bottom cell center positions. Okay.
Not clear. I mean, what did you say again, please?
Basically, average the top and bottom cell centers.
The horizontal in the polygon or the triangle,
yeah,
inside of the triangle.
That's just average of all coordinates. That's a centroid. Okay.
Centroid.
Yeah.
Okay.
So for this case, After you solve for the density gradient and Poisson centers, you can use that directly in the integral I4 there, because that's an element-based integral, so that can be directly used. But in addition to that, you also need to find the density gradient and the side centers. Okay, that's for the momentum equation. You need to solve momentum equations later. So for that, then you need to do another set of averaging. Pick a side center and then just average around its two adjacent elements there, and of course you need to do proper vertical interpolations. Okay, slide number 19. This is another explicit term included in I4. It's horizontal viscosity term. I'm not going to spend too much time on it because most of the time we don't even use it. But the way we interpret this is involves second order derivatives. So we use linear shape function, so we cannot evaluate it directly. So we basically use a Gauss theorem and cast it into this integral, boundary integral. Yes?
What is linear quadrature?
Linear quadrature. Well, it's quadrature is basically the way you integrate, the method you use to integrate the evaluate do numerical integration. So linear quadrature is the simplest. You just use linear shape function. Yeah. So you get this horizontal viscosity term as a ratio between these two. So on the top, we already used the Gauss theorem and convert the area integral into the boundary integral. So finally, you approximate this ratio by these summations. And inside here, you need to evaluate the normal derivatives of velocity and the side center. So for this, we just simply average again. Across two adjacent elements, and of course everything is evaluated along fixed z plane. So you need to use chain rule to if you use twin coordinates. So next slide, number 20. After all the unknown equations are solved, then momentum equations and transport equations are relatively straightforward to solve because they only involve the vertical direction. So on the top, you can see the momentum equation. Again, we grouped all the explicit term into the bold F. And now eta is also known. So the only unknowns are inside the vertical viscosity term, and we treat that term implicitly. So also we solve the momentum equations and whole levels and side centers. And we experiment in the early stage. We actually experimented solving the momentum equation and the side and loads. But the advantage of solving momentum equations, UV and side centers, is that the boundary conditions really easy to specify. Okay, because and loads, the normal direction is not well defined. Right, it's a corner there. So that's the main reason. But also another reason is that if you do use this kind of staggering scheme, just mimic the Arakawa C grade and enhances numerical stability. Okay, so now you apply a standard Glerkin-Finite element. Now this time it's only in the vertical direction, and psi L are the hand function in the vertical. Okay, then you integrate and then integrate by parts for the vertical viscosity term. You get the boundary terms coming out, and you then on the bottom you can see the discretized equation. H here is finely simple. H is the step function. Okay, just a way to simplify things. The take-home message here is that the matrix is really trivial. It's a triangular matrix along the vertical, so it's very simple to solve. Next slide, 21. Okay, because we use EOM method, we need to, after you reach the foot of the characteristic line, you need to do some kind of interpolation, right? So in order to do the interpolation, you need to find the velocity and loads. Okay, that's the most natural way of doing interpolation. Of course, you can always use this non-conform P1 NC type shape function and do interpolation using this kind of shape function. Then we have actually this kind of option in the version of self. But if you want to convert the side velocity to load velocity, there are a number of options. The first option, of course, is simplest, just average around the ball, as you can see on in this picture. But the disadvantage of this option is that it's most introduce a lot of numerical diffusion, okay, and damping. And the second method is to utilize the linear shape function. So this is a more elegant method. The shape function can be either conformal or non-conformal. Okay, and so for example, the velocity and this node 1 is a summation of this two side velocity minus this side velocity. Okay, if you use the linear shape function, either conformal or non-conformal, they came out to be exactly the same. But the disadvantage of this one is that we got lots of numerical noise. You get numerical dispersion. Okay, there's always constant struggle between the numerical diffusion and numerical dispersion. Okay. So finally, we decided to use some kind of filter to basically get rid of those numerical modes. So I will talk about that in next slides. Slide 22. Okay, so this is a simple filter we use to filter out the unphysical spurious numerical modes. So if you take a side center here, 0.0, and construct a stencil around it, 1, 2, 3, 4, this quad. So the final filtered velocity U0 hat is basically a weighted average of all the points around it. Okay, alpha is the Shapiro factor, and people have proved for at least for the uniform grade, alpha equals 0.5 is best in the sense that it filters out all the subgrade noise, whereas leave the physical signal untouched. So we typically just use alpha equals 0.5. And another thing is that in unstructured grid setting, so this stencil may not be well defined. Okay, so if, for example, in this for this internal sides, okay, for this internal side, you can see that this side center is outside the quad. So you don't want to apply filter here. So what we did, we extend the stencils into neighboring elements, construct well-formed quads. Of course, in the extreme case, if your grade quality is really, really bad, you can even after extending the stencil, the side center is still outside. In this case, you need to edit your grade. Okay. And another case is that if the center is near, if your side center is near the boundary, okay, so you may not be able to extend the quad. That's horizontal boundary there. Okay, so that's where the violation occurs. You need to edit your grade. Usually it's very simple. You just move a load or swap an edge and get rid of those violations. And in the if you use ACE tools, as most of us here in OHSU do, actually there's a button you can press, so it will show you all the violations for the Shapiro filter. And so my advice, practical advice for using the code is that whenever you have a new grid, don't bother to generate all the inputs first. Just get hgrade.gr3 and vgrade.in and param.in and turn on the pre-processing flags inside the param.in, okay, and run the code. They will report all the violations for the filter. If you use the linear shape, the second option I mentioned in the previous slide. Okay, if you use simple averaging, then the code will run with any grid. Okay.
So, how does I'm not following the diagram of how the stencil.
In the ideal case, this is what a stencil looks like.
Okay.
This point is inside the quad, right? You want to make sure this point inside the quad here. So in many cases it's not. Then you need to either extend the stencil or edit your grid.
Okay.
Make
so
sure.
So the 0 point is
Yeah. The blue points. Yeah, the blue points is a velocity. That's a point of concern.
Okay.
Yeah. Yeah. You want to filter the velocity.
If the grid is orthogonal, is there any problem for this one?
If the grid is the question is if the grid is orthogonal, then would you have this problem? Actually, I haven't thought about that. Probably not. Near the boundary. Yeah, I'm not sure. Near the boundary, you probably still have this kind of violation to deal with. But the inside, for internal sides, if the grid is orthogonal, you shouldn't have this problem at all. Yeah, but I have to think about it carefully. Yeah. Next slide, 23. Okay, so we typically, by default, we use linear shape functions and photo characteristic line for EOM methods. Okay, so this is for the momentum equation. Okay, and of course, the linear shape functions will not introduce any dispersion, diffusion, but will dispersion. That's right. But it will introduce not numerical diffusion or dissipation. So one option to bypass this problem is to use the higher order Kriging methods. And so this picture on bottom shows you an example of a stencil used in Kriging. For this case, is a two-tier Kriging cloud. So the cross represents the position of the foot of the characteristic line. Okay, and all the color nodes around it are used to construct the Kriging cloud. Kriging is a statistical tool based on best linear unbiased estimation of a random function, but it's an exact interpolator in the sense that the functional values are preserved at the Kriging points. Okay, so it's different from least square. So the way Kriging works is to decompose an arbitrary function f into two components, drift and a fluctuation. So for simplicity, we use a linear drift function. And the fluctuation function involves a so-called generalized covariance function, which is the function of the distance in between two field points. So the choice of a generalized covariance function can be really arbitrary, but those are the typical generalized covariance function people used. You can go as high order as you want. So the essence of Kriging method is to minimize the variance of the fluctuation part. By doing that, you get this set of algebraic equations. You can solve them, then you get the approximation. The good thing about Kriging is twofold. Okay, the number one, it does not assume anything about Kriging points or cloud. Okay, so that's really important for unstructured grid because you cannot assume anything for the distribution of nodes. And then number two, if you look carefully, this algebra equation system, the matrix actually is consists of a bunch of geometric quantities that will never change unless you change the grid. So you can invert the Kriging matrix once and use it again and again during time stepping. So it's actually a very efficient method. And with some simple benchmarking, we actually showed that with Kriging, significantly improves the velocity accuracy. So this is something you probably want to try. And another thing I want to point out is that the Kriging EOM methods are different between the serial and the parallel version. For parallel version, we use this two-tier Kriging cloud, whereas in serial, the Kriging cloud can be multi-layer, can be multi-tier. Okay, you can extend the tier of Kriging cloud as much as you can, as far as the grid is concerned. So the reason we did this is because in the parallel version, we want to preserve the efficiency. Okay, so if the stencil becomes too large, then you have to do lots of communications. So that's why we restricted cloud to be two-tier. Next slide, number 24. After the elevations are solved, the horizontal velocities are solved. The vertical velocities are usually solved from the 3D continuity equation, okay, using the finite volume methods. They, because we are using uneven prisms, so you need to be careful how you calculate the vertical advective fluxes. Okay, so this is what you get from the finite volume discretization. Okay, so you basically, like I said, finite volume is a special case of finite element. You just use piecewise constant shape function. So each term in this equation represents fluxes from various faces, and you solve this from bottom, that's the bottom boundary condition, all the way to the surface. That's how you get the vertical velocity. Here, for the last equation, dB dt, the B is the bottom deformation. Okay, just in case you use bottom deformation modules, the bottom may be moving, so that's the velocity there. Next slide, 25. So I mentioned that the inundation, the wetting and drying can be treated very easily inside the self. There are actually two algorithms inside self to deal with wetting and drying. Okay. After elevations are found, then you need to update the z coordinates and the free surface positions for the next time step. So there are two algorithms to do that. The first one is the simplest. You just go through the element size and loads at the end of each time step based on and update their indices based on newly computed elevations. Okay, but this may sound simple, but there are some rules you must follow, which I will talk about during the next lesson when I talk about the code. Okay, so you need to stick to some rules for consistency. The second algorithm is slightly more complex, but it's usually more accurate if your grid resolution is fine enough. So it's an iterative method, basically. You iteratively try to find the instantaneous wetting and drying interface, a shoreline. So suppose at previous time step, this orange line represents the shoreline. At that time, previous time step, then you go along each point along the shoreline. So suppose at this point, the element becomes wet, then you need to extrapolate the velocity based on some kind of average. Suppose at this point B, all elements become dry, then you need to open it up, then you update the shoreline position, okay, and iterate until you get the shoreline position in the next time step. And after everything is done, then you need to do this kind of constant extrapolation at the final interface. This smooth out lots of numerical noise. Okay, so you basically, suppose it's the final shoreline here, and the elevation at this point will be same at this point. Okay, so that's constant extrapolation. Okay, next slide, number 26. Okay, now we are dealing with transport equation. There are two methods to solve a transport equation. One is using the EOM, the other one using the pure or invariant methods, the finite volume methods. Okay, so the EOM method, of course, has a disadvantage of not preserving mass explicitly, at least. So in this method, you take the transport equation and vertical boundary conditions, and then you apply standard Glerkin finite element method in the vertical, just very, very similar to what you did to the momentum equation. Psi L, again, are the vertical hand function. But this time, what you do something different. You apply mass lumping. Okay, basically you enhance the diagonal. So essentially you are reverting from a finite element to finite difference methods. And this way, you will reduce the bandwidth, number one. Number two, you will reduce the numerical dispersion. Because finite element method, if you use finite element method to solve a transport equation for the tracer, then you may have an undershoot and overshoot. That's not guaranteed. So this is a discretized equation here. And the T star, of course, is a backtracked value. Okay, so in the horizontal, we use this linear shape function, but this time we split each triangle into 4 sub-elements. Okay, the reason we do that is because the linear interpolation is diffusive. So but then the diffusion is related to the element size. The smaller the element size is, then the smaller the numerical diffusion is. So we want to reduce that numerical diffusion. So for that reason, we solve the transport equation at sides and nodes, okay, in order to do this kind of interpolation. And vertically, we use the cubic spline. And of course, horizontally, you can also use quadratic, because you have a 6 point here. You can construct the 2D quadratic shape function. But you must, in that case, you must be careful to minimize the numerical dispersion, because the higher order interpolation is always leads to dispersion. Okay. So the second algorithm to solve the transport equations is the upwind methods. It's finite element method, finite volume methods. So you basically take the basic computational unit, and that's a 3D prism, and integrate the transport equation within each prism. Okay, then you get a finite difference, a finite volume discretization in this form. So important thing here is that the vertical diffusivity form is term is treated implicitly to enhance stability, and horizontal is explicitly. And this is a source term. But the most important thing here, as far as the transport equation, is the advection term, how you treat the advection term. Okay, so here on the left, second term on the left-hand side, you can see the summation of advective fluxes across 5 faces of the prism. Okay, Tj star is still undefined. Okay, we need to find a way to evaluate Tj star. So we threw out all the irrelevant term, all the easy terms. We just concentrate on the advection. And because you use flux form, so the mass is conserved at element level, right? But just because mass is conserved doesn't mean that the maximum principle is also preserved. Maximum principle basically says that the maximum or minimum of the tracer must not exceed the initial condition. Okay, if you only have advection and diffusion, that means in the absence of a source of sink terms. So that's one of the basic principles in physics. So in order to get the maximum principle right, you need to utilize the 3D continuity equation. So one of the key steps in this solution is to really enforce consistency between the your upwind method and the 3D continuity equation, the way you solve for the vertical velocity. Okay, so this is actually the way you solve vertical velocity. Basically, sum of all fluxes equals 0. Net flux is 0 because there's no source or sink term inside, right? So this is actually the way you solve for the vertical velocity. And of course, you can split this into two terms, inflow and outflow. So inflow must balance outflow, right? That's what this equation is about. So in upwind method, Tj star is taken from the signal upwind, literally upwind, okay, where the signal travels from. So Tj star is either Tj or Ti, depends on the phase is inflow or outflow. Okay, that's the. And the T here, by the way, the tracer are defined at the present centers. Okay. So Tj, Tij is here. So Tj is somewhere next to it. Okay, either vertically or horizontally. So next slide, 28. So now you plug that upwind approximation into the advection equation. So then you regroup terms according to if it's outflow or inflow. And you can see that this equation basically says that the tracer concentration and next time step is a weighted average between some tracer concentrations previous time step, right? You can, this is abstract form. You know, this is a constant, this is a constant. So it's a weighted average. So if the weights are all positive, then maximum principle obviously preserved, right? If it's a true weighted average, then the maximum and the minimum are definitely preserved as you go from time step to time step, right? So that's how you get this Coulomb number condition. Okay, maximum principle is related to the Coulomb number condition. So that places a limit to the maximum time step you can use. Okay, so this is a Coulomb number condition, Vi over the summation of outgoing fluxes. So this applies to a particular prism. Of course, you have to make sure this condition is satisfied for all prisms. So the final time step you can use is the minimum of all the allowable time steps calculated from this Coulomb number condition. So in practice, this condition can be very severe, and especially in shallow water region. Okay, the horizontal advective flux wouldn't cause too much problem, but the vertical advective flux can be a real pain sometimes, because in the shallow region, especially near wet and dry interface, your vertical thickness can be very small, so your denominator can be very small. I mean your denominator can be very, your numerator can be very small. Yeah. So in order to bypass that severe constraint, we basically, because the upwind method is linear, so we can actually treat part of the flux, the vertical flux, implicitly, so without violating the maximum principle. So that's what this is a final equation we use. We basically separate out the vertical advective flux and treat them implicitly to bypass the Coulomb number condition associated with it. And horizontal fluxes we still treat explicitly. Okay, this is the final equation. So upwind method the advantage of using upwind method is that it preserves mass conservation and also preserves the maximum principle, which are the two basic requirements for transport equations. But the disadvantage of upwind method is lower order, it's first order, and it's very diffusive. Okay, so far we haven't talked too much about the source term, but very briefly, like slide 29. One particular the source term, the body force is due to the solar radiation for the heat transfer equation. So for this term, we basically use simple finite difference along the vertical, okay, here, in order to satisfy the mass conservation. And the important point is that right on the bottom, for the bottom prism, we zero out this H dot term. So basically, we are treating the bottom as a blank body, absorbing all the heat. Okay, so we did this in order to preserve the mass conservation, because otherwise the bottom will leak out some heat. But the drawback of doing this is that in shallow water depths, because the bottom absorbs all the heat, it can heat up very quickly. You can have a very high temperature. So one way to bypass this problem is to use a larger albedo for the shallow region. Okay, so in the newer version, allow users to specify that variable albedo. Any questions so far?
And how much larger? Just depends on your situation.
Yeah, typically inside the estuary in the shallow region, say shallower than 2 meters, I just immediately jack up the albedo to be about, say, 90%, 0.9. Yep. Okay, so the third method to solve the transport equation is similar to the upwind method, but it's a second order. TVD stands for total variation diminishing. So it's a way of saying enforcing the maximum principle. Okay, so essentially what it says is that total variance or L2 norm cannot increase over time. Okay, that's the criteria used in TVD. So let's start from pure advection equation, because other terms are easy to treat. Again, we need to find a way to approximate this TJ star. But now, instead of only using the upwind component, we will also use some downwind component. Okay, so this is a blend of upwind and downwind. Phi j is so-called flux limiter function, varies between 0 and 2. If phi j equals 0, that's upwind. If it equals 2, that's downwind. If it's, phi j equals 1, that's central scheme, right? Central difference, because the average between the upwind and downwind. So the key step in TVD method is to find a local value for the flux limiting function, such that the maximum principle is preserved. So I won't go too much detail here, but essentially you basically manipulate some terms and put them into similar form as upwind term here. Okay, you do this kind of manipulations. But now delta and lambda here are nonlinear functions. So it's TVD method is nonlinear methods. So this is unfortunate because we can no longer treat the part of the flux, advective flux, implicitly, because it's nonlinear methods. And after some manipulation, you combine terms into this kind of term. It looks really familiar because it looks really similar to the upwind method. So what this equation essentially says that the new tracer concentration is a weighted average of old concentrations, right, around it. So the maximum principle or Coulomb number condition is satisfied if all the weights are positive. Okay, so you get this Philo Coulomb number condition. If you compare that with the upwind method, you can see only difference is this 1 plus n plus. N plus is number of phases for positive for outflow. So you can see that the upwind method, the stability constraint is more severe. Not only that, like I said before, you can no longer treat the vertical advective flux implicitly. That would definitely violate the maximum principle. So that's just unfortunate. That means if your application has some shallow regions in it, then the time step must be very small because of this constraint. So that's why TVD is not very efficient if you have a shallow region. Okay, so one of the important things in TVD, if you read the literature, especially one-dimensional things, is this upwind ratio. Okay, so it's basically ratio between the upwind and upwind. Okay, upwind of the upwind. So two-tier labors. So this is the upwind ratio. So if you read literature, this depending on whether or not this ratio is large or small, the flux limiter function will react to that. If it's large, that means you have a very sharp gradient propagating in. So you better use upwind like. You need to reduce the flux limiter functions. If it's very small, then you can use downwind scheme without violating the maximum principle. Okay. Any questions about TVD? I know this is a very brief introduction. There's a lot of details in there. Next slide, 32. Okay. So the advantage of TVD, the same as a upwind, it conserves mass and preserves the maximum principle. But disadvantage is that it's not very efficient if your application has a shallow region. If your application, if your domain depth, the depths are all large, then TVD is not that bad. It's a reasonably okay method, and it's a second order accurate. So it does not have much numerical diffusion in it. And because the maximum principle is concerned, you don't have to worry about the numerical dispersion. There's no undershoot and overshoot. It guarantees that there's no undershoot and overshoot. That's a good thing about TVD. And in terms of choice of flux limiter function, here are some popular choices. Okay, but in principle, if you look at the diagram, any functions that falls within this region can be a candidate for flux limiter functions. So the super B is, of course, one of the most popular, but it's also most compressive, meaning that if you have some gradient, you sharpen the gradient. You tend to sharpen the gradient. And min mod, on the other hand, is the most diffusive, okay, closest to the upwind, and Van Leer and Osher are somewhere in between. There are actually other types of flux limiter functions out there. Okay, the turbulence closure equations. They look very complex, but the way to solve them is actually very straightforward. We basically just treat them as transport equations. And in this case, we even neglect the advection part because that's not dominant part. The source term and sink terms are dominant part. So we don't have the complication of advection here. So here is the example of how you solve the two equation Umlauf and Burchard closure. As you call, K is the TKE, and psi is related to the generic length scale. And here are on the right, you can see the vertical boundary conditions, and the essential boundary condition form and the natural boundary condition form, both. The reason is that originally we only have essential boundary condition, but after consulting with the Galton folks, they like to impose the natural boundary conditions first and override the bottom value with the essential boundary condition. I don't know why they claim that it's more stable. But if you apply standard finite element method along the along the vertical, then you can easily utilize the natural boundary condition. Okay, for the vertical boundary condition. The only thing, and TKE and psi, K and psi are defined as nodes and whole levels. Okay, and then diffusivities are defined at half levels. They are staggered because diffusivity are used in momentum equation or the transport equations. The half levels are more natural. So this is a discretized the closure equations. We treat the vertical mixing term implicitly, and the key thing here, the key difference from the transport equation is the way you treat the production term. Okay, the sum of the shear and buoyancy term. And again, we consulted with the Galton folks. They basically treat this term either implicitly or explicitly, depending on its sign. You know, if it's a negative, you treat it implicitly. The reason is actually very simple, because if it's the whole thing is negative, you put it back to the left-hand side, it becomes positive. So you basically enhancing the diagonal, make it more stable. Okay, I think that's the reason they do that. These kind of tricks.
Joseph, could
Yes.
you say again, this is about the treat explicitly or implicitly, depend on, you said the sign?
Yeah, sign
Did you say
of,
that?
yeah, the sign, whether the total production term is positive or negative. If it's negative, you treat them implicitly. If it's a negative, then you treat, if it's a positive, then you treat it explicitly. Yeah.
Depend on the sign of the total production.
Yeah, so
if it's a positive, you treat it implicitly.
if it's a positive, you treat it explicitly.
Explicit, okay.
Yeah, you want to,
Got it.
yeah.
And you said the reason is simple. The sign, why the sign has to do with explicit and implicit?
Because if it's, the question is why you treat it this way, implicit or explicit, depending on sign. Because if you look at the discretized the equation on the bottom, if the sign is negative, the term becomes negative. You treat them implicitly. You need to move them back to the left-hand side. That would actually enhance the diagonal.
Oh, okay. It has something to do with diagonal.
Yep.
Okay.
So enhance the numerical stability.
Numerical stability. Okay.
Yep. Yep.
Thank you.
Sure. So the second equation looks complicated, but it's essentially the same thing. So in the itself actually been linked to this Galton turbulence closure library, and Galton is a general ocean turbulence model. It's a one-dimensional water column model with lots of biology linked to it. So we really like to use. We don't want to reinvent the wheel. Because Yumnov and Burchard actually built this library. So we thought, just use the existing tools we can have. But recently we found some perplexing problems with this Galton library. So in a shallow region, sometimes you get NAN coming out. I suspect it's a division by zero or overflow, underflow problem, and detected by the main self code. And the funny thing is that it's really platform dependent. Some clusters do not report this problem, whereas other clusters are very susceptible to this. So so that's just unfortunate. I like to point out, because we really don't want to reinvent the wheel here. It's something you may want to take notice, because In case in your application you use a Galton and then you get this NN coming out, you know what's happening. So.
Joseph, excuse me, I have one more question about turbines.
Sure.
Okay, I missed that the natural boundary condition. First is what is the natural boundary condition? Secondly, is that symbol you use there? I'm not sure I can read very well.
Okay. So if you look at the upper right corner,
right?
Those are the boundary conditions in the essential boundary conditions. And below that,
okay.
Yeah, those are the essential boundary conditions. K equals something and psi equals something, right? That's the essential boundary conditions. And below that, you have natural boundary conditions. That means there's no flux for the TKE.
Okay.
No flux for TKE near surface or bottom. Whereas fluxes are prescribed for the generic length scale, the psi.
Okay, so it was multiplied by nu, and then there's that's 5k subscript represent the
that's
k of 5.
That's the diffusivity coefficient, so it's not power. Okay.